Hi, this is Yingchao. Today I would like to present our project on behalf of my team member, Sungmo and Ellie. So my topic is about approximating a general service by deployable origami structures using neural network. So let's get started. So first I want to talk about the background. Origami, the art of folding paper, has in recent years become really powerful and popular for building mechanical metamaterials and provide valuable design guidelines for morphing structures. The left side is a really famous origami-based space structure that capable of deformation. It is star-shaped. And the right side is one potential application for rigid flat foldable quad mesh origami structures. It's like researchers are trying to simulate the human face by folding the origami pattern. The human face is really complicated, so the task is really challenging. So our project is to address the inverse problem of approximating a generic surface using a deployable origami structure through machine learning techniques. Specifically, we aim to use the convolutional neural network, CNN, to learn the highly nonlinear relationships between the geometric properties of the surface and the geometry of the origami pattern. So that is the architecture of our CNN. The input data is the 32 by 32 by 6 tensor, and you can comprehend like an image with 6 channels. And the output is a long vector. One of them is the folding parameter omega, and the left 266 are the folding angles along the boundary, along the L shape, the sector angles on the boundary. So we have 4 convolutional layers and 4 max pooling and 2 fully connected layers and 1 flattened layers. So let's talk about the data generation. We generate 40,000 data by a forward algorithm. So by using the forward algorithm, we feed into the sector angles and the folding angle, and the forward algorithm can spit out the deformed origami pattern for us, and we can calculate the first and second fundamental forms. So right now we want to solve the inverse problem. We give the first and second fundamental form. Can we obtain the origami crease pattern and deform pattern to approximate that surface? So we have manipulated with lots of hyperparameters. We just showed 2 of them here. So at the end of the day, we use the learning rate 10⁻⁴, regularization parameter 10⁻⁷, and we use 5 kernel size instead of 3, which can capture the neighboring information better. And we use the pooling operation, all of them are X pooling. And we use the mean square error loss with L2 regularization as our loss function. So we plot some sample training data to see the first and second fundamental form, how it look like, and that is a learning curve. So you can see the training and validation losses decrease rapidly at the start and dropping before around 500 epochs and converge at around 2000 epochs. The training loss around 10⁻⁵, and validation loss around 8 times 10⁻⁵. And we have also calculated generalizing testing error. It's around 7.4 times 10⁻⁵. It's really small, and it gives us a really good prediction for test data. So we have presented 2 representative testing samples with the prediction result and the true label. You can see that the surfaces are really similar to each other, and you can also see the similarity of the first and second fundamental form and the small test mean square error, which shows a good prediction of our CNN. So but when we turn to the canonical surfaces, there's 2 results can kind of show the good approximation in some local areas, but overall, the first and second fundamental form are not that accurate than we have done for the test data. So we have difficulty in approximating certain surfaces, and we have gaps. And we try to develop a generalized data set by adjusting mountain value assignment and to put more general data. And we improve the training process, and we can also enhance the input data for CNN because we do not explicitly consider Gaussian curvature before, and we can incorporate that. And we want to implement generative models like diffusion models and conditional game before. Thank you.